Hello there, Mr. Sutton here, bringing you the BC Calculus 7-2 Extra Practice Number 1 solutions on Maclaurin series. For this problem, we want to find the fourth order Taylor polynomial for this function about x equals 0, and then use it to approximate f of 0.2. So we're starting with 1 minus x quantity to the negative 2. Let me get the general setup for my Taylor polynomial. So this is going to be, p sub 4 is going to be f of 0 plus f prime of 0 times x. Next we have f double prime over 2 factorial x squared, f triple prime 3 factorial x cubed, and the fourth derivative of 0 times x to the fourth over 4 factorial. So we need to find all these derivatives and the function value. Function value, f of 0, that's just 1 minus 0 to the negative 2. That just comes out to 1. And now the first derivative, we're going to have negative 2 times all this stuff to the negative third times a tail of negative 1. So that ends up being a positive 2 out in front. And then we're evaluating all of this at 0. So this is just really just 2 times 1, which is 2. Next, for my second derivative, I've got negative 3 times 2 and a tail of negative 1. So that's 6 when all is said and done. I'm actually going to write 3 factorial out here, though. Because you're going to see as you keep going, you just keep multiplying by the next number, so it ends up being a factorial. That's going to help us simplify this a little bit later on. So I'm going to write 3 factorial 1 minus x to the negative fourth evaluated at 0. And then that's just going to be 3 factorial, because you're just doing 3 factorial times 1. Next, for the third derivative, yeah, there's a pattern here. Now we're doing negative 4 times all this with a tail of negative 1. So that ends up being 4 factorial times all this to the negative fifth. Evaluating that at 0, we've just got 4 factorial. And does anyone want to guess what the next derivative is going to be? So multiplying by the 5 then, this ends up being 5 factorial times all this to the negative 6. Evaluate at 0, we've got 5 factorial. And we are now ready to plug things in to our Taylor formula here. So for f of 0, we again just had 1. And then for f prime of 0, that was 2, so we have 2x then. Plus, this is going to be 3 factorial over 2 factorial x squared. We can simplify that to just 3x squared. Next, we have 4 factorial over 3 factorial x cubed. Well, that just simplifies to 4. And then we've got 5 factorial over 4 factorial. That's just 5x to the fourth. So there's our fourth order Taylor polynomial. Now to approximate 0.2 in this function, I'm going to write f of 0.2 is approximately p sub 4 of 0.2. And now I'm actually going to plug it in on the calculator now that I've shown people what I'm doing. So I've got that whole polynomial plugged in my y1. Let me quit out of there now and do alpha trace to pull up my y1. And now I'm just going to plug in 0.2. And hope for the best. Enter. Comes out to 1.56. On this problem, they want us to find the second order polynomial at x equals 0 for the tan function. So let me start by finding f of 0, f prime of 0, and f double prime of 0. F of 0, tan of 0 in other words, is just going to be 0. Next, for f prime evaluated at 0, well, f prime is just secant squared of x, evaluated at 0. So secant of 0, that's going to be 1 over cosine of 0. Cosine of 0 is just 1. So 1 over 1 is just 1. Squaring 1 still gives us, you guessed it, 1. So that's what all that comes out to. And then finally, we need the second derivative. So that's going to be, let's see here, we're going to have to use the chain rule. This is going to be 2 secant x times the derivative of secant, which is going to be secant tan. So that ends up being secant squared of x tan of x, evaluated at 0. And since you're plugging 0 into tan here and getting 0 out of that, this whole thing goes to 0. So plugging things in, we've got f of 0, which is just 0, plus f prime of 0x, which is 1x. And then we've also got f double prime over 2 factorial times x squared. But since f double prime is 0, we don't end up writing the next term because it's just 0. So our second order Taylor polynomial is just a linear function of x. On this problem, I want the second order Taylor polynomial for x equals 0 for secant of x, so the Maclaurin series. Let me start with f of 0. That's going to be secant of 0, which is just 1 over cosine of 0, which is 1. Next, we're also going to need f prime and f double prime to get second order. That means second derivative. So f prime, that's going to be secant of x tan of x, evaluated at 0. That's going to give us, well, let's see, tan of 0 is 0, so that zeroes everything out. And then finally, we need f double prime of 0. So for that, I'm going to use the product rule. Let me get up my box and ribbon here. I've got secant of x, tan of x, and this is going to be derivative of secant x tan x down here, and secant squared down here. Now, if x equals 0, let me see how that changes the things in my box here. Secant is going to be 1, tan of 0 is 0, tan of 0 just zeroes everything out in that lower left. And then secant of 0 we already saw was 1. Squaring that still gives us 1. So using my ribbon, I've got 0 times 0 plus 1 times 1, which is just a grand total of 1. Putting it all together now, I've got f of 0, which is 1, plus f prime of 0 times x, but that's just 0 times x, which doesn't change anything. And then we have plus f double prime of 0 over 2 factorial times x squared. So that's 1 over 2 x squared. On this one, we're trying to find the second order Taylor polynomial about 0, so the Maclaurin series, for this function. We need f of 0, f prime of 0, and because it's second order, f double prime of 0 as well, so up to the second derivative. F of 0 is just going to be 1 over the square root of 1 minus 0. That's just 1. F prime, I'm thinking of this as being really just parentheses 1 minus x squared to the negative 1/2. Power rule gives me a negative 1/2 out in front. Then we have 1 minus x squared to the negative 3/2 if we subtract 1 from that exponent. But don't forget we also have a tail, the inner derivative of negative 2x. And we're evaluating all that at 0. Now before I go ahead and do that, let me simplify this a little bit. I mean, I know that when I plug in 0 for x, that's going to zero everything out. I know this is going to be a derivative of 0. But I want to simplify this because I'm going to need the second derivative as well. So multiplying negative 2x times negative 1/2, that cancels out the 2's and the negatives, leaving us with just x times 1 minus x squared to the negative 3/2. And now I know that, again, if I plug in 0, this is going to just all zero out. Now for f double prime of 0. For this one, I'm going to go ahead and use the product rule. So the box and ribbon's coming out here. Here's my box. We've got x. We've got 1 minus x squared to the negative 3/2. And then we've got derivatives of 1. And let's see here. This is going to have a derivative of 1 minus x squared to the negative 5/2. And I have a negative 3/2 that's coming out down in front. Don't forget, though, we have a tail of negative 2x, and that would happen every time you take the derivative of this thing. I could simplify that, but I'm about to go ahead and plug in 0 anyway for all the x's. So I think I can do that pretty easily without simplifying it. So if x is 0, in the upper left we have just 0. Over here we've got, let's see, 1 minus 0 to some power. That's just going to be 1. Down here, 1 is 1. And here, plugging 0 in for this x out here zeroes out everything because we're multiplying by 0. So using my ribbon now, I've got 1 times 1 plus 0 times 0. That's just going to be 1. All right, time to go back and put everything in my formula. So I've got f of 0, which is 1, plus f prime of 0 times x. That's 0x, so we're not going to write that. Plus 1 over 2 factorial x squared. And that's all we needed because we needed second order. For number 3, I'm trying to find the Maclaurin series for f of x equals sine of x. So let's start by doing f of 0. That's going to just be 0. Now we'll do the first derivative at 0. So that's going to be cosine of x evaluated at 0, which is 1. And now the second derivative, that's going to be negative sine of x evaluated at 0, which comes out to 0. Third derivative, that's going to be cosine of, or negative cosine of x evaluated at 0, which is negative 1. And for the fourth derivative, now we've got sine of x evaluated at 0, which is going to be 1, or 0 rather. So it starts over. And then we've basically got this pattern continuing, because then I'd get a cosine, a negative sine, and a negative cosine again. So I'm going to have a 1 for the fifth derivative, sixth derivative is 0, seventh derivative is negative 1, and we could keep repeating the cycle. But I think at this point, let's start writing down some terms and see if we can find enough of a pattern to write the general term of this series. So we start with a 0. We don't have to write that. This is going to be 1 times x right here, because this is our first derivative of 0 times x. And then our second derivative is 0, so we don't write the next term. Third term, we've got minus x cubed over 3 factorial. Next, we have a 0, and then our fifth term, that's going to be plus 1x to the fifth over 5 factorial. Sixth term is zeroed out. Seventh term is going to be negative x to the seventh over 7 factorial. And I think we can definitely see a pattern here. So we are going all the odd exponents and factorials, and we're alternating. So we need to come up with a way of capturing that in our general term. Since we're alternating, we're going to need a negative 1 to some power in there. It's either going to be the n or the n minus 1. And then we need to have a way of saying x to all the odd exponents. So I'm going to just write down the general term for you, and then I'll explain what I just did. I think that's easier than trying to explain it in advance. So here's my general term with my, this actually should be a plus, just to keep this plus-minus pattern going. All right, so here's what I did. I'm going to start by getting all the odd exponents, and then I'll explain this negative 1 piece. So to get all the even exponents, I would just do x to the 2n, because multiplying anything by 2 makes it even. If I want all the odds, then I just do 2n minus 1. To get all the odd numbers, I take all the even numbers and just subtract 1 from all of them. Now, I also could have gotten all the odd numbers by adding 1, so you really have to kind of figure out which way you're going to go on this one. But now, if I've committed to doing it this way, then that means my first term, my first n that I would be plugging in, would be n equals 1. If I have x to the 2 times 1 minus 1, that would just be x to the first power, which would give us this first term. Now, this first term needs to be positive. So when I'm figuring out my negative 1 to some power, I need to make this the n minus 1 power. That way, if I plug in 1 for n, I'm doing negative 1 to the 0, which will make this come out positive. Just to make sure that this continues working, let's say I plug in 2 for n to get my second term. So now I've got negative 1 to the 2 minus 1, which is negative, which is what we wanted. And then we have x to the 4 minus 1, or x to the third. We've got 3 factorial, and so that's exactly what we need for that term. And we'll go one more just to keep making sure that this works. So plug in 3 for n. Now I've got negative 1 to the second power, which is positive again. Up here, I've now got x to the 6 minus 1, or x to the fifth, with a 5 factorial down below. All right, so this works. For this problem, they want the Maclaurin series for f of x equals e to the x. So that means the first few terms plus the general term. So we need f of 0 to start with here. That's just going to be e to the 0, which is 1. We need f prime of 0. Well, f prime of x is also e to the x. Plugging in 0 to that still gives us 1. In fact, every single derivative, since you keep getting e to the x and plugging in 0, every single derivative at 0 is just going to be 1. F double prime, f triple prime, the nth derivative, all 1. So it's always just going to be 1, and then you might have a factorial to divide by with your x's. So we've got f of 0, which is 1, plus f prime of 0 times x, so plus x, plus f double prime over 2 factorial with an x squared. So that's x squared over 2 factorial. Plus we've got, this is going to be 1x cubed over 3 factorial for that next term. And we could keep going. In general, we have x to the n over n factorial with a bunch of dots in there. For this problem, we want the Maclaurin series for 1 over 1 minus x. So that means we need the first few terms, and we also need to figure out the pattern and write the general term. Let's start with f of 0, and then we'll just take as many derivatives as we need to here. F of 0, that's just going to be 1 over 1 minus 0, so just 1. For f prime, I'm going to think of this as being 1 minus x to the negative 1 power. So then if I use my power rule, that's going to be negative all that stuff to the negative 2. But I have a tail of negative 1 from the inner derivative, so that just becomes a positive 1 out in front. So when the dust settles, we just have positive 1 minus x to the negative 2, evaluated at 0. And by the way, as you keep taking derivatives, you're going to keep getting an inner tail of negative 1 that cancels out the negative from the exponent. So we're just going to write positive numbers out in front from here on out. Also, when you plug in 0 to all of these, you're always just doing 1 minus 0 to some power, which is just always going to come out to 1. So this comes out to 1. The second derivative, that's going to be a 2 out in front, exponent of negative 3. That's going to come out to 2 times 1, so that's 2. For the third derivative, we've got a 6 out in front now. Plugging in 0, that's going to be 6. And just to get a little bit more data in here, because these derivatives don't seem to have a predictable pattern just yet, taking another one, we've got, this is going to be 24 positive out in front, 1 minus x to the negative 5th. So evaluating that at 0 gives me just 24. All right, we can go ahead and write out our series now. We've got f of 0, which is 1. We have f prime of 0 times x, that's 1x that we're adding. Next, we have, this is going to be, let's see here, 2 over 2 factorial x squared. So that's just 1x squared. Then we have 6 over 3 factorial x cubed, but 6 is 3 factorial, so that's actually just x cubed. Then we have 24 over 4 factorial, which is essentially 24 over itself, x to the 4th. And at this point, I think we can see the pattern here, because the derivative always just so happens to cancel out the factorial that's built into the formula. So this just ends up being plus dot 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 plus x to the n plus dot dot dot. For number 5, we've got a true-false question. If this series here is the Maclaurin series for some function f, then f prime of 0 equals 1. Justify your answer. All right. So we don't know what this whole function actually equals or is equivalent to. It's not a geometric function, not a geometric series. So we can't just turn it into some real function and then take the first derivative and plug in 0. We have to know a little bit about how Maclaurin series are constructed. Now we know when we're building a Maclaurin series that f prime of 0 is the coefficient of your linear term. So it's always f prime of 0 times x. So that means since up here we just have 1x, f prime of 0 must equal 1, which means that their thing that they're saying here is true. For this problem, we have all sorts of information about the function f at x equals 0. Based on that, we want the third order Taylor polynomial generated at x equals 0 for f of x. Okay, so I'm going to write out my general Taylor formula here, just going out to 3 derivatives because they said third order. So I got f of 0, f prime of 0x, f double prime of 0 x squared over 2 factorial, and f triple prime of 0 x cubed over 3 factorial. So now going through, because they gave us all the information we needed, we had f of 0, which they told us was 0, so I'm not going to write that. F prime of 0 x, well that's just 1 times x. F double prime of 0 x squared over 2 factorial, well they said f double prime was 0, so I'm not going to bother writing that quadratic term. And finally, f triple prime of 0 is 2, so we have 2 over 3 factorial, which is really just 2 over 6, or 1/3, and then we have an x cubed there. So that's going to match with answer choice E. On this problem, we're given this series here, that's the Maclaurin series for some function f. We want to know which of the following gives us the 12th derivative of 0. So a Maclaurin series is a Taylor series that's constructed about x equals 0. So really, we just have to find the 12th derivative that goes into building this series. So for that, I'm going to ask about the coefficient of x to the 12th power, because that's where the derivative, the 12th derivative of 0 is going to live in this series. So our x to the 12th coefficient ought to have the form 12th derivative of 0 over 12 factorial. Just using our general Taylor nth term formula, that's what the coefficient ought to look like. What is the actual coefficient of x to the 12th in the series that they gave us up here? Well, if you look at the pattern, and it's easier to see with this third term here, the exponent is always 1 higher than the factorial. And, this is really x squared over 1 factorial, which is 1. This is x to the first over 0 factorial, which is also 1. So that's why you're not seeing anything on those first two terms. So this means that if I'm looking for the x squared coefficient, that's going to have a factorial 1 lower than 12. So that's going to be 11 factorial. And there's nothing in the numerators. This is just 1 over 11 factorial for that x to the 12th coefficient in the actual series. At this point, we're just going to multiply by 12 factorial to isolate the 12th derivative. So that's going to be 12 factorial over 11 factorial. Well, this is really just 12 times 11 factorial in the numerator. That's how these factorials work. The 11 factorials cancel, leaving us with just the 12 out in front. So that ends up being choice E.